Good afternoon. So my name is Triou. I'm from the astrophysics department of CEA in Saclay. So I'm going to talk to you about the evaluation of the performances of a spectro imaging detector to be embedded on board a nanosatellite for solar flare studies. So the contents of my talk is the following. First, I'm going to present you the CALISTE detectors on their application for space astrophysics. Then I will show you the studies that we made in CEA of the use of the CALISTE of detectors on board the nanosatellites for solar flare studies. And then I'm going to quickly show you the requirements for the accommodation of all the nanosatellites of such detectors. First, the heritage that we have in CEA on CDT detectors for space applications. In 2002, we had the first detection plane in space made of CDT on East-Green instrument on board Integral. And since then, we have had the R&D program in CDTE, which made us improve the sensitivity of this detector by a factor of 100, and the energy and time resolution, as well as low-level thresholds, are 10 times better now, and the spatial resolution is increased by a factor of 6. So here you will see the focal planes that we had on East-Green, and here the focal planes that we're able to make now with CALISTE detectors. So now the performances of such detectors. So on this plot we see the increase of performance between 2001 and 2012 in terms of spectral resolution. So for example at 60 keV we have 0.6 keV resolution. And we can do a high-resolution spectroscopy over a large energy range, since, for example, at 600 keV we have 3 keV energy resolutions. And on this table we have the other characteristics of the CALISTE HD. Okay. So with this detector we can make imaging. And here we see a prototype in our laboratory. So the CALISTE is put in an enclosed vessel with a void, and we use a coded mask, a very small dimension here, like less than 8 centimeters, and we can do imaging this way. Now we can also do polarimetry with CALISTE, because this detector is pixelized. So I remind you the principle. And so there is, when polarized light arrives, there is quantum interaction in the hit pixel and a photoelectric interaction in the scattered photon in another pixel. And of course, since the detector is very thick, the diffusion angle is close to 90 degrees. And so we made experiments at the European Sequential Radiation Facility to test our detectors, this capability to measure polarization of X-rays. And we had such results. So we here have the same kind of curve that was presented in the previous talk, and we see the comparison between the theoretical curve and the measurements. And so here is a picture of what we had measured. And with this method, we can estimate the polarization angle with an accuracy of less than 1 degree, and the degree of polarization of less than 5%. So the perspectives of these detectors So we will use a variant of CALISTE for solar orbiter on the STIX instrument. So that is a spectrometer telescope for X-ray imaging. So we will detect X-rays from 4 to 150 keV and make, as Diego said previously, X-ray imaging with a Fourier inverse transformation method. So the flight production of these CALISTE detectors are in progress. So we see that CALISTE are miniature and high-performance detectors, and that they can therefore be used on a nanosatellite for science. And the objective that we have to use them on a nanosatellite is first technological, to use the CALISTE detector in space before solar orbiters, and also scientific, that is to perform simultaneous observation of solar flare together with solar orbiter. And we will do imaging and spectroscopy with solar orbiter, and spectroscopy and polarimetry with the so-called big nanosatellite. So now I'm going to present you the study that we made to accommodate these detectors on board a nanosatellite to study solar flare. So on this movie we see we see a solar flare as seen with a RECI. So here we have the thermal radiation in red, and in blue we have the brainstorming radiation, which is a high X-rays, as Diego said previously. So here is the plot that you already saw in the talk of Diego. And so for bright eruptive event observation, we will use CALISTE HD on a satellite as a counter, and a spectrometer, and also a polarimeter. So that is a big project. So to make our study, we first analyzed the solar flare events. We made an analysis to estimate the flux that the detector will receive. So we estimated the solar flare fluxes in the CALISTE energy range, taking with analyzing the flare data from GAUSS and RECI satellites. And so we estimated also the flare frequencies depending on their class, that we see here, and also their duration. And following this study, we have estimated the flux that the CALISTE detector will receive. Then we have made a simulator that modelizes the detector and its response to solar flare. So the detector parameters are its readout time, its latency time, its low-level threshold, as well as the characteristics of the filters we can put in front of this detector to reduce the flux. So here we have the incoming solar flare flux, and if we simulate the response of the detector, we have the number of counts per second that the detector will measure with and without features. So here in this plot, we can see that if we add a feature, we become more sensitive to the high energy photons, because we know that filters are more efficient at low energy, so that we will have more counts, more high energy counts if we add a filter. Also, we will avoid saturation of the detector due to the low energy photons that are more numerous. Okay, so on this slide, I represented the count rate of the detector versus the flare flux, because of course we have to make the detector operate in a region in which it is not saturated. And we see that we have to limit the flux of the incoming flux below a given value, so that the detector behaves as a good spectrometer. Because if we increase the flux, we will have many photons arriving on the detector during the latency time of the detector, and if we increase, so this is from this area, and if we increase even more the flux, we will have a pilot effect in the detector. So to have a good functioning of our detector, we have to remain in this region. And to reach this goal, we can either adjust the low level threshold of the detector, add filters, or reduce the number of pixels that are switched on. So we made this complete study, and we reached a solution. So to perform spectroscopy on a wide energy range, that is between 3 and 500 keV, also to not saturate the detector and have a good incident flux estimate, we propose a payload configuration with 4 CALISTE, and this way we will have a good spectrometer on a wide range of flares. So the configuration is the following. I'm going to tell you quickly. So we'll have the detector 1 and 2 without filters, but we can adjust the low level threshold on the first one and the number of pixels on the second one. And we have a third detector with an aluminum filter in front of it that will be adapted to high intensity flares. And we have the fourth detector with a tantalum filter in front of it that will be adapted to extreme flares. So with this configuration, we can have the detectors operate for a wide range of flares. Okay, so this is an example of how these detectors respond to a high intensity flare, but I'm not going to go into the detail, but just to tell you that the configuration we establish is a good trade-off between the photon flux and the detector electronics capabilities, and it allows to reconstruct the incident photon spectrum, knowing the number of activated pixels, the efficiency of the filters, and the characteristics of the detectors. So now the constraints that we have for the nanosatellites. So to observe the sun, we will logically choose a sun-synchronous orbit, preferably a dawn-dusk orbit, and we estimated that a 3-unit CubeSat could be good for that, and we have our 4 CALISTE detectors as a payload. So we have estimated the volume of science data to download following our study of the flare events and the payload configurations that we have. And we, of course, one event will consist in a maximum of 2 pixel hit to take into account the fact that we can measure the polarization of the redundant. And we consider that we will use X-band, that we have a sun-synchronous orbit, 1 ground station. We took into account the diffuse background, and with all these hypotheses, we see that the telemetry budget in X-band is consistent with all flares up to MX class, that are high-intensity flares. Also, we have estimated the power budget depending on the modes. Also, so the power budget remains below 10 watts for all modes. Also, we have estimated the pointing accuracy that we need. So we will remain in front of the sun, but an accuracy of plus or minus 20 degrees is sufficient. And also the operating temperature. Typically, a nominal temperature of minus 5 degrees is consistent with the good performances of the detector, and also the temperature stability requirement that depends on whether we download the temperature with the count. In such a case, we have no constraint, or if we download a spectrum, and in such a case, we have a constraint on the temperature. That is plus or minus 1 degree over the time on which we do the spectrum. Of course, doing spectrum on board allows reduce the volume of data to download. So as a conclusion, we see that the CALISTE detectors are miniature, high performance, and are qualified for space application and so adapted to nanosatellite. For solar studies, we will have CALISTE SO on solar orbiter and CALISTE HD on the CubeSat, that is a big project to study solar flare. And we will do spectroscopy and polarimetry and also stereoscopic observation with solar orbiter. And the accommodation constraints are consistent with CubeSat capabilities. So the collaboration that we have for this project is CALISTE for the detectors, and EPFL in Lausanne and FHNW for the platform design, and possibly a Clyde Space for the satellite development. Thank you very much.
Thank you. Any question? I have one question up there.
I would have one again. Did you already started to do a thermal analysis, or is it currently more before that analysis done? So is this currently only estimated that you are in -5 degree range, or you already did some analysis? I mean, you want to have a completely sunlight orbit with -5 degree CubeSat temperature. So did you do a thermal analysis for your satellite to see if it's in that temperature range? Or
you mean the temperature requirements?
Yes.
You're talking about the operating temperature here? Or? I don't understand.
Yes, it's the temperature.
Okay, so we since we know our detectors, I mean, you mean the constraint on the orbit or the?
Yeah, over the combination.
Okay.
I mean, you produce 7 watts,
okay.
and you have to
So up to now we didn't do a complete thermal study taking into account the orbit and everything. So this is something that has to be done. But I mean, I think it's something that could be easily reached, and if not, we could think about having a Peltier cooling system. But of course, it's power conditioning. So, but this study has to be done. Up to now, the study that we did is to check that we can make a payload to do good science.
Okay, thank you.
All right.